this lesson, we're going to go over how we can perform different operations on radical expressions and rational exponents. So before we really start, we want to just make sure that we understand the terminology since we're going to be using this throughout. When we have a radical, the radical is the symbol that we see. Inside the little corner of the symbol is your index, which is the little number that's written there. If there's not a number there, that just means that it is a 2. Underneath the radical is your radicand. So that is the expression or the value underneath the radical. When you have an exponential, you have a base that's raised to an exponent. First, we're going to look at multiplying radical expressions. When you're multiplying radicals, you have to have the same index in order to multiply. So remember, the index is the little number inside the little check mark. Then we want to multiply any coefficients, multiply the radicands, and then keep the same index, and then we just simplify if we can. So for the first example, we have the cubed root of 6 times the square root of 2. So we can see that we can't actually multiply this together because our indexes are different. This index is a 3, this index is a 2. Since the indexes are different, we can't multiply this. So our answer would just stay cubed root of 6 times square root of 2. Okay, in the second example, we can see that the indexes are the same. We have the cubed root of negative 4 times the cubed root of 2. Both indexes are 3, so we can multiply. So what we're going to do is keep the radical with the index, and we're just going to multiply the radicands. So we're going to multiply negative 4 times 2, which gives us negative 8. Now the cubed root of negative 8 can be simplified, and that's going to equal negative 2. Okay, so now we're going to look at a couple of other examples. Same idea. Okay, so first we check the indexes. The indexes here are the same, so we can multiply. So we're going to multiply the coefficients first. So 4 times 5 is going to give us 20. Then we're going to keep that radical with the index, and then we're going to multiply the radicands. So when we multiply the radicands, we have 2 times 6, so that's going to give us 12. We have x times x, which is going to give us x squared, and then we have y to the 5th. So now we've gotten one radical, and now what we want to do is simplify this radical. So we're going to use our knowledge from last class. The 20 is going to stay on the outside. I'm going to break down whatever I have inside to try to find pairs that I can pull out of the square root. So 12, the square root of 12 is really the square root of 4 times the square root of 3. So since 4 is a perfect square, we really have 2 times 2 times 3. That's going to equal 12. And then we have x squared, and that is even, so it's divisible by 2. So I'm going to divide it by 2, and that gives me x times x. So remember, we're adding like x to the first times x to the first to give us x to the second. Now the y to the 5th, 5 is not divisible by 2, but 4 is. So we can break this into y to the 4th and y. So y to the 4th, if I'm looking for pairs that I can use to multiply to give me y to the 4th, that would be y squared times y squared. But that's going to equal 4 y's, and I have 5, so I have 1 extra y. So now when I go to pull out anything that's a pair, they're going to join the 20 on the outside. So I have a 20 that's on the outside, that's going to stay. I'm pulling out a pair of 2's. So whenever I join things together, I'm going to make sure that I multiply them. So the 2 is going to come out. I have a pair of x's, so the x is going to come out. And I have a pair of y squareds. So y squared will come outside. And then on the inside, I have a 3 and I have a y. So 3y. So just to kind of make this a little bit simpler, I'm just going to multiply this together. So this will give me 40xy squared, square root of 3y. Okay, so we look at the next example. We check all the indexes. They're all the same, so we can multiply. There are no coefficients. All the coefficients are 1. So 1 times 1 times 1 is just 1. So I'm going to multiply the numbers. 2 times 5 times 10. That's going to give me 100. X cubed times x squared. So I'm adding 3, 3, and 2. So that's going to give me x to the 8th. And then I have y times y cubed times y. So I'm going to add 1, 3, and 1. So this is going to give me y to the 5th. So now I have one single radical, so I'm going to then break this up. So 100 is a perfect square, so I can write that as 10 times 10. X to the 8th is even, so it is divisible by 2. So I'm going to make this x to the 4th times x to the 4th. And then y to the 5th is similar to the previous problem. So 5 is not divisible by 2, but 4 is. So we're going to make this y squared times y squared with one extra y left over. So now when I go to pull out my perfect squares, I'm looking for groups of 2. So I'm going to pull out a 10. I'm going to pull out an x to the 4th. And I'm going to pull out a y squared. And then what I'm left with is just this y on the inside. When we're multiplying rational exponents, the same rules of exponents apply to rational exponents. So if the bases are the same, we're going to keep the base and add the exponents. If the bases are not the same, we're going to multiply the bases and keep the exponent. So as long as the exponents are the same, we can do that. So let's look at these two examples. So number 1 here, we have 7 to the 1/4 times 7 to the 1/5. Now here we have the same bases. They're both 7s. So what we can do is keep the base the same, so keep the 7, and then we're going to add the exponents together. When I add the exponents together, I have fractions. Remember that when we add fractions, we need to make sure that we have a common denominator. So in this case, my common denominator would be 20. So I need to multiply this first fraction by 5 and the second fraction by 4. So this is really going to be 7 to the 5 over 20 plus, oh my goodness, and then 4 over 20. So this is going to equal 7 to the 9 over 20. In the second example, we don't have the same base. The 2 and the 5 are not the same, but the exponents are the same. So here the exponents are both 1/2. So when the exponents are the same, we can multiply the bases, so 2 times 5, and keep the exponent. So 2 times 5 is going to give us 10. So this is going to be 10 to the 1/2. When we're dividing radicals, you must have the same index in order to divide. Okay? And you can choose to either use one giant radical or split the fraction into 2 radicals, the top and the bottom. Typically, it's going to be easiest to do one giant radical. Then you divide the coefficients, you divide the radicands, you keep the same index, and then you simplify. So if we look at this first example, I have 8 square root of 54x to the 5th divided by 4 square root of 3x to the 3rd. Now, I could simplify the top and I could simplify the bottom separately, but what's going to happen in that case, because this bottom, the 3 is not a perfect square and the x to the 3rd is not a perfect square, I'm going to end up with a radical in the denominator, and that we don't really want. We want to see if we can make it so that there is no denominator. So when you see something like that that might not work doing it individually, make everything one big radical. So what I mean by that is I'm going to say that this is the same thing as 8 over 4 times the square root of 54x to the 5th over 3x to the 3rd. By writing the fraction as one big radical instead of a radical of the top and a radical of the bottom, we can simplify what's underneath the radical first before we simplify. So we're going to divide any of our coefficients. So 8 over 4 is going to give us 2. Because I've written this as one big radical, what I can do now is divide everything that's inside. So 54 divided by 3, that's going to give me 18. And then x to the 5th over x to the 3rd, because I have the same base of x, I'm going to subtract my exponent. So 5 minus 3, that's going to give me x squared. And now I just have one radical. I don't have any more fractions, anything in the denominator, and now I'm just going to simplify. So the 2 is going to stay on the outside. 18 I'm going to break down, so I know that that's the square root of 9 and the square root of 2. So the square root of 9 is going to be 3 times 3, and then times 2. And x squared is even, so I can divide that by 2, so it's x times x. So I'm going to pull out this pair of 3's, I'm going to pull out this x. So on the outside, I have the 2 that was originally there, times the 3 that comes out from that pair, times the x that comes out from that pair, and then I have a 2 left over. So I have 6x square root of 2. Okay, so we could do it separately with the top simplify it, the bottom simplify it, but then we're going to have more work to do. So we want to make sure that we try to do this the easiest way that we can. So in number 2, we have the cubed root of 162y to the 5th over the cubed root of 3y squared. So again, I am going to rewrite this as one big radical. 162y to the 5th over 3y squared. So this is going to make it a little bit easier for us because now I can actually divide what's inside. So 162 divided by 3 is going to give me 54. And then y to the 5th over y squared, I'm going to subtract 5 minus 2. So this is going to give me y to the 3rd. So then what I'm going to do here is break this up. So since I have a cube root, I need groups of 3 of the same number. So for 54, that is 3 times 3 times 3 times 2. That's 27 times 2. So I'm going to have 3 times 3 times 3. There's that group of 3 of the same number times 2. And then for y cubed, that's going to be y times y times y. So I'm going to pull out a 3 from this group. I'm going to pull out a y from this group. And then I'm left with the cubed root of 2. When we're dividing with rational exponents, the same rules of exponents are going to apply to rational exponents. If the bases are the same, keep the base and subtract the exponents. So in the first example, we have x to the 3/2 divided by x to the 2/3. The bases are the same, they're both x, so we're going to take x to the 3/2 and subtract 2/3. Because we have fractions, we want to make sure that we have a common denominator. In this case, it will be 6. So I have to multiply the first fraction by 3. So that's going to give me 9 over 6. Second fraction, we're going to multiply by 2. So that gives me 4 over 6. So 9 over 6 minus 4 over 6 is going to give me x to the 5 over 6. Okay, in the second example, we have x's and y's, but we're just going to take the like terms and subtract those exponents because those are our bases that are the same. So here we have x to the 2/3 minus 1/2 and y to the negative 1/4 minus a negative 1/2, which will become plus a positive. So again, we need a common denominator. So for the x's, we have 6 should be our common denominator. So we're going to multiply the 2/3 by 2. So we get 4/6. 1/2 we're going to multiply by 3. So we're going to get 3/6. For the y, we have a common denominator of 4. So the first one we can keep as negative 1/4, but we're going to change the 1/2. We're going to multiply it by 2. So this becomes 2 over 4. So now I'm just going to do 4/6 minus 3/6, so I have 1/6. Negative 1/4 plus 2/4 is going to give me 1/4. So x to the 1/6, y to the 1/4. When we're adding and subtracting radical expressions, you must have the same index and the same radicand in order to add or subtract. If the radicands are not the same, simplify the radical first, and then add or subtract the coefficients only, leaving the radicand as is. So in this first example, square root of 5 plus the square root of 10. They have the same index, both indexes are 2, but they do not have the same radicand. Here we have a 5, here we have a 10. So when that happens, we want to see if we can break them down and simplify. Well, we can't simplify the square root of 5. There's no perfect square in there. And square root of 10, same thing. So since we can't simplify this, our answer will just stay square root of 5 plus square root of 10. Okay, in the second one, we have to first check the indexes. So the indexes are the same. They're both square roots. And the radicands are the same. Here we have a 2 and here we have a 2. So since they have the same index and the same radicand, what we're going to do is add what's in front. So we're going to add the coefficients. So in front of the square root of 2, we have a 1. Right? So even though it's not listed, we know there's a 1 in front of here, and there's a 3 in front of here. So 1 square root of 2 plus 3 square root of 2 is equal to 4 square root of 2. So we keep the square root of 2, and we don't do anything with that. We just add the numbers in front. For this third example, we have the square root of 27 plus the square root of 3. So we check the indexes. Both indexes are the same. We check the radicands. They are not the same. Okay? But the square root of 27, we can rewrite that because the square root of 27 is going to be 9 times 3, and 9 is a perfect square. So this will become 3 square root 3. So now that we've simplified the square root of 27, we do now have the same radicand. We have both 3's on the inside and the indexes are the same. So now we're just going to add the coefficients. So 3 plus 1 will give us 4 square root of 3. Okay, so we're going to look at these. Here we check the indexes, they're the same. We check the radicands, they're the same. So 3 minus 2 is going to give us 1 square root of 5x. So you can put the 1 in front, but you don't really need the 1 there. It's understood. So we'll just leave it as square root of 5x. Number 5, indexes are the same, radicands are not the same. So we're going to rewrite the square root of 12. So again, that's going to be, let's see, 4 times 3. So the square root of 4 is a perfect square. So we're going to pull out a 2 square root 3. Now we have the same radicand. They're both 3's. So we can add the coefficients. 5 plus 2, that's going to give us 7 square root of 3. Okay, and then for number 6, here we have cube roots. So the cubed root of 250, so that's going to be 125 times 2. So 125 is a perfect cube, that's 5. So we're going to rewrite that as 5 cubed root of 2. Because if you notice, they all have 3's as the index, but all of their radicands are different, so we want to break them down. The cubed root of 54, well, that's going to be 27 times 2. And 27 is a perfect cube, so that's going to be 3 cubed root of 2. And then 16 can be broken down into 8 times 2, and 8 is a perfect cube, so that's going to be 2 cubed root of 2. So now we have all of the radicands are the same, so we're just going to combine the coefficients. So 5 plus 3 minus 2, that's going to equal 6 cubed root of 2. Foiling radical expressions involves foiling as you normally would. When you multiply two radicals with the same radicand, that will result in the radicand number outside of the radical. So for instance, the square root of 2 times the square root of 2, because they're the same number, the shortcut would be just 2 outside of the radical. It's 2 because we get the square root of 4 since we multiplied 2 times 2, and the square root of 4 is a perfect square. So we can kind of cut out the middle step. As long as you have the same number under the radical and you're multiplying them together, it's just going to be the number inside the radical without the radical. And then we combine like terms. So for the first example, we're going to FOIL. So 3 times 5 will give us 15. 3 times the square root of 7. So we're multiplying 3 times the coefficient, which is 1. So that's going to be 3. And then the square root of 7 just gets tacked on. Negative square root of 7 times 5. So I'm multiplying negative 1 times 5. So that's negative 5 square root of 7. And then negative square root of 7 times positive square root of 7. So I'm multiplying the numbers in front, negative 1 times 1, so that's going to be negative 1. Square root of 7 times square root of 7 would be square root of 49, which is 7. So now that we have this written out, we can combine like terms. So 15 minus 7 is going to give us 8. 3 square root of 7 minus 5 square root of 7 is going to be negative 2 square root of 7. So when we write our answers like this, we want to make sure we have the number without the radical first, and then the number with the radical second. Okay, so let's look at the second example. So again, we're going to FOIL. 4 times 5 is going to give us 20. 4 times 4 square root 2, we're going to multiply 4 times 4, so that's going to be 16 square root 2. 2 square root 2 times 5, so we're going to multiply the 2 in front with the 5, so we get 10 square root 2. And then we're going to multiply 2 square root 2 times 4 square root 2. So multiply the numbers in front, 2 times 4, that's going to give us 8. Square root of 2 times square root of 2 is going to give us 2, right? Because it's square root of 4, which is 2. So now this is really 16. So now I'm going to add 20 and 16. So I have 36. And then 16 root 2 plus 10 root 2 is going to give me 26 square root of 2. Okay, and the last thing we're going to look at is how we can rationalize denominators. So we want to get rid of radicals in the denominators of our fraction. We don't want to ever have radicals in the bottom, so we have to rationalize them. If there's only one term in the denominator, then you need to multiply the top and bottom by whatever radical expression will cancel out the radical. If there are two terms in the denominator, we want to multiply the top and bottom by the conjugate. Okay, so here are all examples where we just have one term in the bottom. Now, number 1 has 5 square root of 2 in the bottom. Okay, I can't keep the square root of 2 down there. The 5 is fine, but the square root of 2 I can't keep. So I'm going to multiply the top and bottom by the square root of 2. Because I know that when I multiply the square root of 2 times the square root of 2, the radical will cancel out. So what I have here is 2 square root 2 on the top, and on the bottom I have 5 times 2. And what I can do now is simplify. These 2's will cancel out. So I have square root of 2 over 5. Okay, so these are equivalent. It's just that we don't want to have the square root in the bottom. Okay, so for number 2, we have the square root of x in the bottom. So the index is a 2, and right now the exponent on this x is a 1. In order for the radical to kind of cancel out, we need to have an x squared because that's a perfect square that we could pull out. So what I'm missing then is a square root of x. So I'm going to multiply the top and bottom by square root of x. So we get 7 square root of x on the top, and on the bottom, the square root of x times the square root of x is the square root of x squared, but I know that that is a perfect square. So I'm going to pull out the x from the square root of x squared. Now with number 3, because we have a cube root, we can't just multiply by the cubed root of x. We want to think about the exponent that we have. So in the denominator, we have the cubed root of x to the first. So if I want what's underneath the radical to be x to the third, so it will come out as a perfect cube, I need 2 additional cubed root of x's. So I need to multiply the top and bottom by the cubed root of x squared over the cubed root of x squared, because the 1 plus the 2 is going to give me x to the third on the inside. So when I multiply the top, I get 3 cubed root of x squared. On the bottom, I have the cubed root of x cubed, and that is just going to give me x. So I have 3 cubed root of x squared on the top, and on the bottom, that simplifies to just x. Okay, and in number 4, we have a very similar type of question, but notice that now we have x squared on the bottom, so cubed root of x squared. So if I want to cancel out the radical in the bottom, I'm only missing 1 cubed root of x because I already have 2. So I'm going to multiply by the cubed root of just x, cubed root of x. So when I multiply the top, I have 3 cubed root of x over, this is going to add x squared and x to the first, so 2 plus 1 is going to give us the cubed root of x cubed. So now we have a perfect cube, so I can pull out the x to simplify. So that'll be x in the bottom. Okay, so you just want to see what it's missing and multiply the top and bottom by whatever it's missing to make it a either perfect square or perfect cube. Now here's an example where there are two terms in the bottom. So whenever there's one term, we just do what we did in the last examples. When there's two terms in the bottom, they're separated by a plus sign or a minus sign, we have to multiply the top and bottom by the conjugate. And we've talked about the conjugate before when we had imaginary numbers. The conjugate means we're going to change the sign in the middle. So I'm going to multiply the top and bottom by 5 plus the square root of 2. 5 plus square root of 2. If we started with an addition sign here, then we would use subtraction signs here. It's always the opposite of the sign in the middle. Now the point of doing this is that it will cancel out the regular radical term in the bottom when we FOIL. So we're going to distribute this. So 3 square root of 2 times 5, that's going to be 15 square root 2. 3 square root of 2 times square root of 2. So I'm multiplying the 3 times the 1 in front. So that's 3. Square root of 2 times square root of 2, that is 2. So that's my numerator. In the bottom, I'm going to FOIL. So 5 times 5 gives me 25. 5 times root 2 is going to give me 5 square root 2. Negative square root of 2 times 5 is going to be negative 5 square root of 2. And then negative square root of 2 times positive square root of 2, I'm going to multiply negative 1 times 1, so that's negative. Square root of 2 times square root of 2 is 2. Now notice here, I have 5 square root of 2 and negative 5 square root of 2. That's the whole point of the conjugate. It will cancel out that middle square root term. So now on the top, I'm going to put the 6 first, 3 times 2, plus 15 square root 2 over 25 minus 2, so 23. Okay, so you guys are going to try these 6 problems. So simplify and make sure that you show your work.